So yesterday we finished off talking about bond polarity and net dipoles, or these forces that occur within bonds. So we had three classes. We had nonpolar covalent, and we said nonpolar covalent is when you've got a difference in electronegativity of less than 0.5. Polar covalent is when you have a difference between 0.5 and 1.7. And then with ionic, we've got a difference of 1.7. I meant to show you guys this yesterday, but I forgot to pull up the diagram. You can find these in a variety of textbooks where it will list the absolute electronegativity values for compounds. So in this case, let's look at carbon, which is 2.5, and hydrogen, which is 2.1. Find the difference between those. It's 0.4. Is that considered polar or nonpolar? Nonpolar. A lot of people get confused by that and they say, well, there is a difference. Yeah, there is a difference. It's just pretty minimal, so we consider that to be a nonpolar bond. That's a good distinction to make. And then we talked a little bit about diagramming these. You're welcome to use the partial positive or partial negative, but if I ask you to draw a net dipole, it's often easier to just draw one arrow. That way you're being very clear. So in this case, the net dipole for methanol is drawn with that blue arrow on the left. Are there any questions with the dipoles? Let's do a little bit of a warm-up and practice these some more. So the first question I have for you guys is boron trifluoride polar. What do you guys think? Let's first draw the Lewis structure. I think this will help us. So we've got boron. And boron has 3 valence electrons. So we could have a fluorine sticking up here, a fluorine sticking out over here, and a fluorine sticking out over here. What's more electronegative, fluorine or boron? Fluorine. So we can go through and say this is a polar bond. That fluorine is hogging electron density away from the boron. But is there a net dipole? No. We have to remember that this is planar, right? And these are all 120 degrees apart from one another. So there is no net dipole. This confuses people because there are other examples that might be different. So is ammonia polar? Yeah, so in this case, if we go through and draw the Lewis dot structure, nitrogen has this lone pair sticking off the top. It's got a hydrogen here, and a hydrogen going back into the page. What sort of shape is this? Yeah, trigonal pyramidal. So in this case, it's no longer planar due to that lone pair sticking straight up. So in this case, is there a net dipole? Yeah, and which way is it pointing? Yeah, straight up and down. So we can go through and draw it straight up and down, and you've got a partial positive in near that hydrogen side. So this one has a net dipole. This is why knowing the three-dimensional geometry of molecules is so important, is that oftentimes if we see it, we initially look at BF3 and NH3 and say, well, they look like they're written the same, therefore they should have the same geometry. Not exactly. We have to include that lone pair, which changes things quite a bit. All right, let's try another one. I'm going to have a chlorine here, carbon here, carbon here, chlorine here, hydrogen here, and a hydrogen here. So is this polar, this compound with a double bond on it? Let's think about this. What's more electronegative, chlorine or carbon? Chlorine. So it's going to have a dipole going in this direction because there's a decent difference in electronegativity. Same on this side. Are they going to cancel out? Yeah, because they're on opposite sides of one another. So in this case, there is no net dipole. But let's take another example that looks super similar. Where we've got two chlorines on the same side rather than on opposite sides. Is this compound going to be polar? Yeah, and the important distinction is this double bond, like we saw, can't rotate. It's locked into configuration due to those p orbitals. Both chlorines are pointing in the same direction, so the net dipole for this molecule is going to be additive in that direction, right? So the side with the hydrogens is going to have the partial positive. The side with the chlorines is going to have that partial negative. We're going to get into this, but this is another example of isomerism. Isomerism means that you've got molecules with the same molecular formula, but they're arranged differently. And we're going to spend a lot of time talking about different types of isomers. Are there any questions about dipoles before we go on to intermolecular forces? All right, so let's go on, talk about intermolecular forces. So there's a bunch of different types of intermolecular forces, and I think you guys have covered these in a few of your chemistry classes. But is there a question about?
Yeah, about the previous molecule. If there was a single bond between the carbons, would it allow it to rotate and kind of cancel out or split?
Yeah, exactly. If it were a single bond and it could rotate freely, then the additive rotation would cancel out, right? So we'll get into rotation between single bonds when we get into chapter 4, and that's going to be a big deal. Yeah. All right, so with intermolecular forces, what's the weakest intermolecular force? Van der Waals, or it has like 4 different names depending on what part of the world you come from. Some people call it London dispersion. Some people call it Van der Waals. And other people just call it fleeting dipole-dipole. I'm fine with you guys using any of these definitions. They're just different ways of describing the same phenomenon. And the overall idea behind London dispersion forces is that electrons can't be everywhere at once. Oop. And so let's take an example of this. And in this example, I'm going to have a helium atom. And a helium atom has this big old s orbital there. And let's say at one snapshot in time, you've got an electron on this side and an electron on this side. So we're just taking a camera shot here. Does this have a dipole? Yeah, at one instantaneous moment in time, there is a dipole, meaning this side of the helium atom is more electron rich, and this side is more electron poor. So we just call this a momentary or instantaneous So what can happen is, let's say we've got 2 of these. let's say we've got a helium atom here, we've got our big s orbital, we've got a helium atom over here, and we've got 2 electrons on the left-hand side of each. Whoop. That means over here we've got a delta positive, over here we've got a delta negative, and over here we've got a delta positive, and over here we've got a delta negative. Can you guys see where the attraction is occurring? Yeah, this electron-rich side of the helium atom on the right side is really attracted to the electron-deficient side of the left-hand helium. So we get this interaction occurring. So we get an attraction between atoms. And one thing that kind of bugs me is that we're taught that this is a really weak force. It's not. This can be a very, very powerful force. Has anybody ever played around with a gecko? Yeah, geckos are pretty cool. They can climb up walls. They can even go upside down along a ceiling, so you can see them scamper across the ceiling. The reason they're able to do that is because of van der Waals forces. So they have molecules on the pads of their feet, right? And those molecules have instantaneous dipoles, so does the wall, and they're actually able to stick to them. So the question is, why can a gecko do it, and why can't we do it? Unless you're Spider-Man. It could be weight. Yeah. So if you look at a gecko foot under a microscope, it's got these really, really tiny little ridges. And so their feet have this massive amount of surface area. And surface area is key when we're dealing with dipole forces. So larger surface area equals larger dispersion forces, or equals greater, I should say. This also explains why methane, which is CH4, has a really, really low boiling point. But if you look at oil, which is still carbon and hydrogen, has a really high boiling point. A long oil chain that's made up of hydrocarbons has a huge amount of surface area so that it can stick to other oil molecules, where methane has a relatively small surface area. So it changes the boiling points, right? So let's put this down to larger surface area. I'll just write SA equals higher boiling point. The cool thing is chemists realize that we can manipulate surface area to a very high degree now. We can make ultra-fine structures, and they're actually trying to make gloves that are super sticky, and same with shoes too. So I'm really hoping that one day we'll have Spider-Man gloves, because that'd be pretty neat. So let's take a look at some examples of this. And this is kind of a weird example, but I like showing it. So this is C5H12. C5H12 has a variety of different isomers. We've got one where it's just straight carbons, 3, 4, 5 hydrogens coming off of each end. So this is known as pentane. Pent just means 5 carbons. And then we have another one where there's some branching that occurs. So we've got a CH3 sticking up here and down here. I'm not going to draw out all of the individual hydrogens. There we go. So that's still C5H12. And then we've got another one. Oop. Where we've got a CH3 here, CH3 here, CH3 here, and a CH3 over here. So all of these have 5 carbons, 12 hydrogens. Which one has the greatest surface area? This is weird to think about. Surface area, is it really tight and compact or long and open? Long and open. So in this case, the one on the far left-hand side has the most surface area, even though it has the same molecular force or molecular formula. It has a little bit more surface area than the ones on the right. And we can actually see this with the boiling points of these compounds. So the boiling point of pentane is 36 degrees Celsius. The boiling point of the next one over is 28 degrees Celsius. And then the one next to that is about 10 degrees Celsius. So we have to pay attention to the surface area of molecules, not just their absolute molecular weight. Does that make sense? All right. So what's another type of intermolecular forces, or another intermolecular force, besides dipole-dipole? Or, I gave it away. Besides dispersion. Dipole-dipole. Thank you, Jeff. So the next one we have are dipole-dipole interactions. And these are attractions between delta positive of one molecule with delta negative on another. And in this case, it's not instantaneous. It's a permanent dipole. So it's not that we're taking a snapshot in time. This is fixed in space. So let's take an example of this, where we have carbon and fluorine here. And then we've got a hydrogen sticking up, a hydrogen pointing back, and a hydrogen pointing back there. Which side of this molecule is going to have the delta negative fluorine? So we can draw this in and we can say that this is our delta negative side, this is our delta positive side. We could also use the net dipole arrow to show this. I'm fine with either of those. And then if we've got another one of these molecules, I'll draw it over here. Got a hydrogen sticking down, another one going out. The fluorine on this one also has delta negative, and this one is delta positive. What we end up with, again, is a weak interaction, or stabilizing. So in these molecules, the fluorine is always going to have that delta negative. It's not just there for a snapshot in time, and these molecules will actually line up in a row, essentially. Yep. Yeah, so the last one, when we looked at the helium atom, does the helium atom have a permanent net dipole? No, it's just instantaneous. If we took a camera and snapped a picture in time, it would have a slight dipole in one direction due to an imbalance in electrons, but it's not a permanent dipole. It's not always going to have a dipole going in one set direction. Whereas with this molecule, the fluorine is always going to be the site with the delta negative. On a helium atom, we don't know which site would have the delta negative. It can be anywhere, right? So the big difference is a dipole-dipole interaction is between set dipoles that are static and unchanging. Dispersion interaction is between a fleeting dipole or an instantaneous dipole. Yep.
The other one you have two fluorine atoms.
Yep.
They're in like this. They weren't part of the same structure.
No, and just like in this case, you have two separate molecules, but these individual molecules have permanent dipoles. With London dispersion forces, you have two molecules that are non-polar, but they still interact due to a fleeting dipole. So a dipole-dipole is between two polar molecules. London dispersion is between two non-polar molecules. All right. There's a really special type of dipole-dipole interactions, or dipole-dipole interaction. What is that? Hydrogen bonding. This is a key feature in chemistry. Oops. Let me change colors here. So hydrogen bonding is just a special case of dipole-dipole. What are the conditions we have to have for hydrogen bonding? Yeah, we have to have a hydrogen. Good job, guys. What's the other thing we gotta have? Yeah, oxygen, nitrogen, and a fluorine. So I'm going to add hydrogen in because I think that's funny. Number 1, hydrogen. Number 2, H bonded to fluorine, oxygen, or nitrogen. When I teach Chem 110, I always tell my students to ask themselves whether or not H is on the phone, so you can remember FON. It's a good mnemonic. The last thing that you need that is often overlooked is you must have a lone pair in the molecule, right? The lone pair is what does the hydrogen bonding in this case. So let's take a look at the classic example for hydrogen bonding. Good old H2O. So we've got water here with lone pairs. I've got another water molecule up here. So if we look at all of the individual dipoles, we've got oxygen hogging electrons away from the hydrogens. And so this hydrogen right here has a very strong delta positive. It's very electron deficient because oxygen is one of the most electronegative atoms on the periodic table. Conversely, on this side, we've got an oxygen that's very electron rich. And so essentially what happens is they interact to the point where it almost starts behaving like a bond. That's why we call it hydrogen bonding. This is a strong, I'm going to put bond-like. Interaction. It's so strong, in fact, that in some cases when you have hydrogen bonding, you can't even tell if this is a covalent bond or if that's a covalent bond. This hydrogen, in essence, belongs to both of those molecules, and so this becomes almost like half a covalent bond, and this one almost becomes half a covalent bond. Hydrogen bonds can be incredibly powerful. Yep? So in this case, the lone pair on this oxygen right here is very, very electron rich because oxygen is pulling electron density away from these hydrogens. So this has electrons plus some. And so these are very, very attracted to the hydrogen on the neighboring water molecule, which is very electron poor. And so in essence, these electrons get donated into this hydrogen and stabilize it quite a bit. So we call the lone pair, or this oxygen, a hydrogen bond donor. Or sorry, we call the hydrogen bond donor, and then this is the acceptor. So you always have to have this matching pair between a hydrogen coming off of your fluorine, oxygen, or nitrogen, and then a lone pair as well. An exception? I'm trying to think of a good example of that. Ammonia can hydrogen bond because it has a lone pair. There are some weird examples. I'd have to get back to you to think of an example without a lone pair. Yeah. All right, so the idea behind hydrogen bonding has been around forever. We're realizing more and more that the idea that it has to be absolutely fluorine, oxygen, and nitrogen isn't entirely true, but they cover 95% of the examples out there. There are some hydrogen bonds where it's a hydrogen even attached to a carbon, but that carbon is super electron deficient. So hydrogen bonding is kind of a catch-all phrase, but it's used to describe a very, very strong dipole-dipole interaction. So let's make a chart. So on one side, we've got London dispersion. In the middle, we've got dipole-dipole. And over here, we've got H bonding. We can go through and we can say that these are stronger. And they have a higher boiling point. And over here, they are weaker. Whoop. And they have a lower boiling point. All right, so now I've got a head scratcher for you guys. Does water exhibit London dispersion forces? Yeah. And it's a weird thing to think about that if you have H bonding, you not only have H bonding, but you've got dipole-dipole and you've got London dispersion. Essentially, it's a catch-all for all of the weaker forces below it. If you have London dispersion, however, you don't necessarily have hydrogen bonding. I think it's something that's not taught a lot, but 25% of the attractive forces between water molecules is due to London dispersion forces. And I'm going to abbreviate London dispersion forces there. So London dispersion forces, like I said, can't ever be neglected. They do play a pretty powerful role in everything. Yep.
I'm confused because it kind of seemed like the London dispersion is just for like single atoms.
So London dispersion, that's a good point. This is always between nonpolar molecules or atoms. So let's say we've got helium. Helium by itself is always going to be nonpolar. And so in this case, if we have two helium atoms next to each other, they're only going to exhibit London dispersion forces. If we run into the case of a dipole-dipole interaction, it does have a dipole, and so it exhibits the dipole-dipole interaction and London dispersion forces. Does that make sense? So dipole-dipole and H bonding are between two polar molecules, and they contain London dispersion forces as well. Yeah. Okay, so now let's do some in-class practice. And what I want you guys to do is to determine the intermolecular force. Yeah. I want you guys to determine the main intermolecular force, meaning the strongest intermolecular force. And then I also want you to predict between the pair of molecules that I draw, which one has the higher boiling point. Is it okay if I scroll up? Okay. So the first example I have is CF4. And the next one I've got CCl4. So which one has, or first name the IMF, or the intermolecular force. And two, determine which has the higher boiling point. So what's the primary intermolecular force in CF4, carbon tetrafluoride? London dispersion. Why is that? Yeah, because all of those fluorines are pulling in equal and opposite directions. So we could say, okay, in this one it's London dispersion. What about carbon tetrachloride, the one on the right? It's the same. Okay, so now we're in a tiebreaker situation. Which one has the higher boiling point? Okay. So with London dispersion forces, what causes something to have stronger London dispersion forces? More surface area. Which of these between fluorine and chlorine has more surface area? Chlorine. So in this case, that's exactly what we observe. Carbon tetrachloride has a boiling point of 77 degrees Celsius. And carbon tetrafluoride is actually negative 128 degrees Celsius. This is a combination of not only weight, but surface area. Chlorine is much, 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 much bigger than fluorine. Yeah, so if you remember back to periodic trends, if we go down a column, you get bigger and bigger atomic radii. And so because chlorine has the bigger atomic radii, it's going to have surface area. Yep. All right, let's do another one. I've got oxygen with two lone pairs. CH3, H and CH3 versus this one. Let me draw in the lone pairs too. What's going to be the primary intermolecular force for these? Yeah, they have a weak dipole due to the oxygen being more electronegative than the carbon. So the net dipole, if we were to draw it in, is actually going to be down towards these lone pairs, right? Because this is a tetrahedral electronic configuration. Two of the electrons are kind of sticking up, and then the other two carbons are sticking down. And then over here, same thing. So these are dipole-dipole. Which one has the higher boiling point? Why does the first one have the higher boiling point? Yeah, bigger surface area. So in this case, you can use mass, but it's not just mass that really matters. You also have to look at the complete surface area. So in this case, the boiling point for the one on the left is 68.5 degrees. 68.5 degrees. The one on the right is 35 degrees. All right, let's do... Yeah. So with hydrogen bonding, you can have carbon elsewhere in the molecule, but the hydrogen needs to be directly attached to an oxygen, nitrogen, or fluorine. Yeah. Okay, let's do another one. We'll do one last one. So let's do this one versus this one. Compound on the left, what's the main intermolecular force? Dipole. Because it has a permanent dipole pointing down towards the fluorines. The hydrogen on the top isn't canceling it out. So in this case, it does have a permanent dipole. What about the one on the right? H bonding. All right, so which one should have the higher boiling point? The one on the right. So in this case, methanol has a boiling point of 65 degrees Celsius. The one on the left is negative 82. So even though the one on the left has very strong dipole-dipole interactions, they're nothing compared to hydrogen bonds. Hydrogen bonds are far and away stronger than dipole-dipole alone.
There was a point at which like a small molecule of hydrogen bonding would be overpowered by a huge molecule with just
Yeah, that's a good question. So if you look at water, water is a really small molecule like in hydrogen bond. It boils at 100 degrees. If you take oil tar, that's a hydrocarbon, meaning it only has London dispersion forces, that might take a couple hundred degrees to boil. So there are occasions where London dispersion alone can trump hydrogen bonding, but they tend to have to be very, very big molecules. Yeah. So what I'm saying is, if I had a beaker full of this, what would its boiling point be? And if I had a separate beaker full of methanol, what would its boiling point be? So I'm not saying we're mixing them necessarily. I'm just saying by themselves, what's in it. So essentially what would happen is we'd have another molecule next to it, and we'd get a weak hydrogen bond occurring between two methanol molecules. All right, so I think we're going to leave off there. When we come back next week, we're going to do a little bit on solubility of organic molecules, and then we're going to go straight into our quiz.